Okay. Then let me share my window. No, this one. Okay, so you can share my screen, right?
Yes, sir.
Okay, good. Then I will start today's proceedings. Let me switch to conversation, chat dialogue, chat box. Okay, fine. So last week, actually, I met with some 7-8 students, and we decided to skip that online session because there are very few attendees. In any case, I have mailed you the solutions. So I hope you have got it, right?
Yes, sir.
Okay, good. So these NP completeness proofs that was covered in this last week's tutorial, these are actually difficult. It's difficult to ask these things in a time-bound exam. Okay. But given the importance of those problems, particularly the subset sum problem, and to some extent the max cut problem as well, you should know these results. Even if you do not follow the proof entirely, have some idea how this thing can be done. And I have also sent you a note containing another NP completeness proof, that is 3 colorability of graphs. That is also an interesting result, but then proof, I mean, NP hardness proof is rather difficult. Okay, but you can go through it if you choose. It's good to know that there are some such complicated proofs. But anyway, today, what we will do, we will mostly cover exam-like questions. So the complexity of today's exercises are, I would say, perfectly suited for our online exams that we have been going through. Okay, so let's start with our first problem. This is not exactly an NP completeness proof, but it's an interesting result about complexity classes. If it happens that P is equal to NP, then you show that every non-trivial problem in this common class, now P is equal to NP. Okay, so every problem in this common class is NP complete. Every non-trivial problem. So do you remember non-trivial problems? This was covered in your, what is that called? Flat course. What is, when do I call a problem non-trivial? Rice's theorem, do you remember?
Why it's not an identity function?
Yeah, so that means there are some acceptance instances and also some reject instances, at least one of each. Okay, so that is called a non-trivial problem. So it's not a problem such that every input is accepted or every input is rejected. It's not like that. Some input is accepted, some input is rejected. Okay, so that kind of problem is called non-trivial. So now you think about this for a couple of minutes, and maybe after at around 3:19 or 20, you suggest me some way to proceed. Yeah, any suggestion?
So, like, we can sort of prove this by contradiction. Let's say P1 is some problem that is not NP complete and P2 is a problem that is NP complete. Now, P1 can be reduced to P2, but and if we reverse the reduction, then P2 can be reduced to P1. And since P2 is in NP, and it's also in P in this case.
No. Remember this thing. So these are like we have done in the flat course. Here also, I would say these reduction algorithms are many to one. So these are not necessarily invertible.
Oh, I see.
This is why these are called many to one reduction. Maybe I give you systematic way of doing it. First of all, you have to show that every non-trivial problem in this common class is NP complete. So let us take any let P be okay. This P and this P it looks like the same. Maybe I use some other letter. Okay, maybe pi. Be a non-trivial problem. And NP. Of course, I am starting with the fact that this is a problem in NP, and therefore, in order to prove that this is NP complete, it suffices to prove that it is NP hard. Okay, so it suffices to prove that pi is NP hard. That is, for any, by definition, for any problem, let's call Q in NP, there exists a polytime reduction to pi. Okay, this is what I want to show. Now I have to use two facts that are given. One, P is equal to NP. So Q is in NP means Q is in P. This is one fact. So P equal to NP implies Q is in P, since P is equal to NP. And the second fact that I will use is that pi is a non-trivial problem. Okay. So by definition, that means there exists some accept instance, let us call IA of pi, and there exists some reject instance for pi. That is what non-trivial means. Okay, now can you suggest something? How shall I propose the reduction? So the reduction from Q to pi. How do I proceed? Actually, these two facts are sufficient. No suggestion?
So we run the algorithm of Q. If it accepts, we return something from IA. Otherwise, we return something from IR.
That's it, right? So Q, okay, not Q. Okay. On input I, run a polytime algo for Q. So this is the first step. And since this is a polytime algo, this runs in time polynomial in the size of the input I for Q. Okay. If the algo accepts, return IA, else return IR. So why is the second step also polytime? This is the only thing that you need to argue.
As it like given if we already know an IA and IR, then
These are actually constants, right? It has this IA and IR behave like constants, maybe very large constants, but they are still constants and absolutely independent of the size of this I. Yes or no?
yes, sir.
Okay, so this is basically a constant time effort in terms of the size of the input I for Q. So this is polytime, this is constant time, so the total is a polytime algorithm. And the fact that this is a valid reduction is obvious, right? If accept, then this pi will also accept IA. If this algo rejects, then this IR, that is also rejected by any algorithm of pi. Okay. So simple, but you just have to do some kind of sequencing of the definitions and whatever hypothesis you have. Happy or not?
Yes, sir.
Okay. So So now let us look at a few real life examples of reduction. Okay, this is actually a bad problem, but a celebrated problem. This is called the graph isomorphism problem. So two graphs G and H are given to us. They may be both directed or both undirected, doesn't matter. So they're called isomorphic if there is a one-to-one correspondence between the vertices of G and the vertices of H, such that whenever there is an edge in G between U and V, or from U to V, depending upon what kind of graph it is, I have the corresponding vertex in H for U, the corresponding vertex of V in H, that corresponding edge must be there in the edge set of H, and conversely. Okay. So for example, if you look at this graph, something like a star-shaped graph, this is basically a 5 cycle. So 1, 2, 3, 4, 5. These two graphs, although they look somewhat different, they are isomorphic. They are both 5 cycles. Yes or no?
Yes, sir.
Okay, so this is called the graph isomorphism problem. On the other hand, if I added some extra edge here, maybe like this, then this graph would remain non-isomorphic, would become non-isomorphic. So why is this problem? GI is graph isomorphism problem. Why is it in NP? So whenever you want to prove certain thing is in NP, there are two ways. The better and more, I would say, conventional way is to provide a certificate. Provide a certificate so that it is polytime, rather it is of length polynomially bounded by the input size. And also you should convince that this certificate for a member in the accept instances can be verified in polynomial time in the size of the input. So what is the certificate here? Another possibility is you can just propose a what is that called, a non-deterministic polytime algorithm. And we have seen that they are essentially the same. So what should be the certificate?
The mapping.
The bijection.
The bijection itself. Okay. The certificate is the map F. So its size is proportional to the number of vertices of G or H. That should be same. And verification involves only these things. Take an edge in G, apply F, find out this, and also you may have to do the reverse thing because this is an if and only if condition. So that can be done in time polynomial, or I would say in time linearing the number of edges plus number of vertices, something like that. Okay. Okay, so next question is actually a bad question. So what do you know about graph isomorphism? Is it NP complete?
It is famously not known to be.
Yeah, so the problem is that it is not known to be NP complete. That is the status.
So what happened to that person who had given a proof in 2015?
Yeah, so there was a proof, Laszlo Babai, right?
Yes, sir.
Maybe this spelling. So actually this person proposed something like a pseudo polytime algorithm. It's not a fully polytime algorithm, but pseudo polytime algorithm. for this graph isomorphism problem, and it was proposed, as you mentioned, maybe in 2015. I do not know whether this is now universally accepted or there is some problem with the paper. Frankly speaking, I do not know. Whatever it is, graph isomorphism problem is not known to be NP-complete, and it's usually believed to be a little bit easier than NP-complete. Even if perhaps not polynomial time, maybe pseudo polynomial time or something like that, but it's believed to be easier than NP-complete. So a proof for the NP hardness of the graph isomorphism problem is unlikely to exist. Okay, so let us not worry too much about this graph isomorphism problem, but let us now look at a similar problem, which is called the subgraph isomorphism problem. So this is something like this. Given two graphs G and H, it's essentially asking the question whether you can embed H in G. Okay, somehow you map vertices of H injectively to vertices of G, such that for any two vertex U and V in H, the edge U comma V exists if and only if that injective function F satisfies that Fu comma Fv, that edge in G exists. Okay. So I am not demanding the G and H to be fully isomorphic. What I am now demanding is that a copy of H, a complete copy of H, should reside in G. This is the subgraph isomorphism problem. And it turns out that although this looks similar to the whole graph isomorphism problem, it turns out that this is a difficult problem. It is NP-complete. Okay, so first of all, subgraph isomorphism is in NP because the certificate is the function F. That map F. So now you think a little bit, maybe for a couple of minutes, why this problem is also NP hard. Yeah, any suggestion?
So we can have a reduction from the click problem.
Yeah.
If we say we have a graph G and we have to find the click of size at most k, then
At least
we can reduce it to the subgraph isomorphism problem with G being the same graph and H being a complete graph of size K.
Okay. So this is last position if instead of if and only if. Which question are you talking about? Oh, this one. This if and only if.
Yes, sir.
Yeah, why
Yes.
only?
Sir, because there might exist an age in G that is not present in H.
Okay, so you are talking about something which is not in the range of f.
Yes, sir.
Okay, but this
Sir, got it.
clearly in the range of f. Okay. Yeah. Okay, so this is, I think, a good idea. In fact, I can also reduce Ham cycle to it. Click to subgraph isomorphism. So let's say G comma R is an instance of clique. So I'm essentially trying to find out whether this graph G has a clique of size R or greater than equal to it. Doesn't matter. From this, I will generate G comma the complete graph on R vertices. So this G contains a clique of size R if and only if G has a subgraph isomorphic to the complete graph on R vertices. Of course, here I am using the fact that these graphs are undirected, otherwise clique does not, I would say, make enough sense. So you can use any other particular kind of graph like Hamiltonian, okay, Ham path, Ham cycle, and you just prepare a Ham path or Ham cycle here. So you're essentially asking the question whether G contains a Hamiltonian cycle or a Hamiltonian path. Okay, so Ham path, and if needed, the directed version, Ham cycle, these will all work. Okay, so these are also fine. Okay, good. So subgraph isomorphism turns out to be difficult problem apparently under the assumption that P is not equal to NP, whereas graph isomorphism is not. Okay. Okay. So now comes an interesting problem. I am going to use it in a few of the remaining exercises. So the partition problem goes like this. You are given n positive integers a1 through an with their sum equal to a, which is given to be an even integer. Without loss of generality, we can assume that these are positive integers. Okay, anyway. Or for that moment, let us restrict to positive integers, say 1 through n. Now, the idea is I want to figure out whether these n integers can be broken or partitioned into two groups such that the sum of the elements in each of these two groups is equal to a over 2, exactly half of it. So that means the given collection can be broken down in exactly two equal sized halves. Is it possible or not? So that is what is called the partition problem. And you show that this problem is NP complete. Okay, so first of all in NP, The certificate is the partition itself. So given the partition, you can simply go ahead and make the two sums and compare them. If they are equal, yes. And if partition, so this instance has a solution, then the certificate is that corresponding partition or one of the corresponding partitions. So why NP hard? So you think a little bit and let us come back again. Maybe 2 or 3 minutes later. Okay, so any suggestion?
So this is effectively the subset sum problem.
This is effectively the subset sum problem, but you need to understand one thing.
Okay, it may not be the only way of solving it.
The problem is that this is one very specific instance of the subset sum problem. It is not a generalization. It is a specialization of the subset sum problem. Okay. So whenever I generalize a problem, and if I know that that special variant is already NP complete, so the general version has to be NP complete. Okay, but this is not necessarily true when I specialize. So this is a special case of the subset sum problem. So there is no guarantee that this is going to be NP complete because this is a special case. Okay. But in this case, it turns out that the special case is also NP complete. Okay, so what is the, of course, your intuition is correct, but there is some, I would say, connection. And the most natural problem from which I will reduce is the subset sum problem. So what is the subset sum problem? You are given such a collection and you would like to find out whether you can choose some of the elements from the collection that achieve a total sum of some target T. And in this case, the target is A by 2. Half of the sum.
So given a set and a target T, we construct a new set.
Yeah.
With
So subset sum problem to partition.
Yeah, with sum is 2T, but
S to T, I want to find a new S prime.
and sum is 2T.
That's all. That's all actually. I have to generate some subset S prime, which achieves a, or which contains a subset with sum equal to the total sum by 2 if and only if S achieves, or some elements of S can achieve the target T. So S is an array, S prime will be another array. So this is the generic reduction technique. But because this is not a pair, I can actually remove this parenthesis. Not needed. This is easy but tricky.
Sir, given an S, how do we exactly generate an S prime? I didn't quite figure that part out.
It's easy but tricky.
Oh, okay, fine. That is unspecified yet. Fine.
Yeah, it's easy. But a little bit thinking is needed. Maybe you think for a couple of minutes. Okay, so maybe I give you some initial thing. Let's say the sum of all the elements in S, this S is sigma. And you want to achieve a subsum of T by including some of the elements of S. Yeah. Now think for a couple of minutes. Add an element sigma minus 2T. Then the sum is 0. And this element may be negative. So let us restrict to positive integers. Of course, it doesn't matter if we include negative integers, but let us try to work with positive integers. Yes, this is a good way of thinking, but yeah, stick to the specifications. Something like that you have to do. Yes. Add some elements to this S. Yeah, any other suggestion? Okay, I told you this is going to be tricky. So for example, I can assume without loss of generality, T is less than equal to sigma greater than equal to 0. Otherwise, you know that this problem does not have a solution. So this is not a very interesting instance. So what I will do, I will append just two elements to S. So S prime will be S, and then append two other elements. One is sigma plus T. Other one is 2 sigma minus T. Okay, just append these two elements. So sigma plus T, sigma is positive, T is positive, so this is positive. And I can assume that T is less than sigma or less than equal to sigma, in which case 2 sigma minus T is also positive. And these are all integers. Now, what is the sum of all the elements of S prime?
4 sigma.
4 sigma, so that is even. So this specification is also satisfied. So now we have to show that a subsum of 2 sigma is achievable from S prime if and only if the target sum T is achievable from some elements of S. This is fairly straightforward, right? If I add these two numbers, this and this becomes 3 sigma. It's already bigger than 2 sigma. So the
The subset must contain exactly one of the two.
Yes. So one part will contain this, the remaining part, yeah, this subset will contain either this, or if I consider that part something, the remaining part will contain 2 sigma minus T. Now, okay, so must be in different parts. Otherwise, their sum is already 3 sigma, which is too big. Okay. And therefore, this has a, I would say, slack of T, right? So this has to be replenished by elements of this. I cannot take this. So the part containing this eventually adds up to 2 sigma if and only if S contributes elements whose sum is exactly T. Yes or no? Yes or no?
Yes, sir.
Okay. Yeah, so this is slightly tricky, but this is doable, right? Little bit of thinking will give you a solution like this. I would not say that this is the only possible solution, but there may be other ways of doing this. And this is one of the possibilities. Okay. So that's about the partition problem. Yes, this is yet another interesting problem. In fact, I am covering all these problems, partitioning, bin packing, knapsack, because in the next 1 or 2 chapters, we need these problems. We will use these problems for doing certain things like generating approximation algorithms and similar things. Okay, so the bin packing problem goes like this. So we have n objects, weights W1, W2, Wn, and you are given as many bins as you want, but each bin is with a capacity C. Okay. Now you want to pack all these objects, W1 through Wn, and your goal is to minimize the total number of bins using as few bins as possible. So you may pack W1 with Wn, W2 with W17, and W18 and W19 maybe. So it's not that you have to pack in the order given, W1, W2, W3. So this is that is what is called linear bin packing. That turns out to be an easy problem, but anyway. So you can choose any arbitrary collections of weights and put those weights in each bin, and the capacity constraint in each bin must not be exceeded. Definitely, if there is some weight which is already bigger than C, then you cannot pack everything. So you can assume that each weight is less than equal to C. Okay. If there are some objects which are of weight greater than C, then you simply throw that object. You simply cannot pack those very heavy objects in the bins of limited capacity C. Okay. Now you first note that this is not a problem that immediately qualifies to be in P or NP or something like that, because it is not a decision problem. This is basically a minimization of M. It's a minimization problem. In other words, an optimization problem. Okay. So what this first part shows that frame an equivalent decision problem, but equivalent means in this context this. That is, the decision problem can be solved in polynomial time if and only if this original optimization problem can be solved in polynomial time. So if we can characterize this optimization problem in terms of a decision problem, such that this condition holds, this is solved in polynomial time if and only if the optimization problem is solved in polynomial time, then this is a good characterization in terms of P versus NP classification, for example. Okay, so tell what can be a good equivalent decision problem. Yeah, any suggestion?
We like for given k, we decide if we can pack it in k bins.
Yeah. So whether k bins suffice.
Yeah,
Okay.
and then for finding the minimum n, we just check one by one until it is yes.
Okay. So the decision problem is that given the weights W1, W2 through Wn and C and some M, decide whether M means suffice. Okay. So why is this equivalent in this sense? So let us prove this if says that if the optimization problem can be solved in polynomial time, then this decision problem can also be trivially solved in polynomial time, because the optimization problem will give you the optimal number of bins. Just check whether that is less than or equal to m. Right. So this is obvious. Only if that is, I want to solve the optimization problem given a polynomial time algorithm for the decision problem. So run the decision problem. For m equal to 1, then 2, then 3, dot, 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 until the decider says, yep. Yes or no? So one bin suffice, you ask the decider. One bin suffices, it says no. Two bins suffice, decider says no. Three bins suffice, now let's say that the decider says yes. So then you know that 3 is the smallest m. And that is the solution of the optimization problem. And of course, since each invocation of the decider takes polynomial time, you are multiplying the running time by a factor of n, right? Eventually, n will suffice with respect to this condition or under this condition. So in the worst case, you have to ask up to m equal to n, right? So the running time may become n times the running time of the decider. But the running time of the decider is already a polynomial in n. Multiply that by n, you will get another polynomial of a bigger degree. I mean, the degree is 1 more than the degree of the running time of the decider. That doesn't matter. Polynomial will remain polynomial. In fact, you can also make a binary search instead of asking 1, 2, 3, 1, n, then n plus 1 by 2. Go this. You can increase the running time by a factor of log n, but in this context, it's not a very important thing, because you multiply a polynomial by log n or by n, it will remain polynomial. Okay, so theoretically, it doesn't matter. Yes or no?
Yes, sir.
Okay. So in that sense, these two problems are equivalent. Okay, so now prove that this decision version is NP complete. Okay, again, think for a couple of minutes. Yeah, any suggestion? From partition given 2 bins. Yes, exactly. Intuitively clear, right? So you do, first of all, this is in NP. I will not often mention this. This is clear. Provide a certificate and hard, NP hard. What is that? Partition reduces to bin pack. So the input for partition is A1, A2, AN with A summation AI 1 to N even. Then from this you generate the same instances A1, A2, AN, but you give bins of capacity A by 2 each. Okay. Okay. You also have to specify how many bins you will tolerate. You will allow. That will be 2. Bin packing, this is the decision version. You can pack all these objects in 2 bins, each of size A by 2. If and only if there is a sub-collection which can be packed in a bin of size A by 2, but that's essentially solves the partition problem, and conversely. Okay. Happy or not? Okay, I assume you are happy. Okay, maybe I will just give you the next, yet another important problem. And think we will have a small break. So it's something like this. This is the knapsack problem. So let's say a thief goes to some house and finds objects that he can take, and these are of weights W1 through Wn. And the thief has a notion of how costly these items are. So these are also some profits. Let us call them P1 through Pn. Now the thief has taken with him a knapsack of capacity C only. Okay. So he wants to pack as many objects as possible. Not exactly so. This is not the optimization idea. Okay, so the goal of the thief is to pack objects in the knapsack such that the total weight of the objects packed is not bigger than C, because this capacity is C. And at the same time, the goal is to maximize the profit of the packed objects. Okay. Now there are 2 important variants. One is called the 0-1 variant. So each of these objects, object 1 of weight W1, it has to be packed or completely discarded. A part of that cannot be taken. Okay, so that is called the 0-1 variant, some kind of binary variant. You either take an object or discard it. And there is something called a fractional variant. So for example, the objects may be something like milk, sugar, or rice. So you can take any fraction of that object. So it's not a question of taking the entire bowl of rice, but you can take some amount of it, whatever you want. Okay. So this is called the fractional variant. So this is called the fractional knapsack problem. This is called the 0-1 or the binary knapsack problem. Okay. Now I will tell you the three parts. So you think about all the three parts. This fractional variant can be solved in polynomial time. And the 0, 1 variant is basically once again a maximization problem subject to the capacity constraint. Okay. So provide an equivalent decision version for that 0, 1 knapsack problem and prove that it is NP complete. Okay. So these are the three parts. You think about this. So let us take a small break. I will come back after 5 minutes, maybe around. I'm back. Yeah, let us solve the three parts one by one. What about the fractional knapsack problem? What is your suggestion? How to solve it in polynomial time?
Greedy solution, choose the object with most profit.
This will not work actually. This will actually not work.
Most profit density, pi upon wi.
Yeah. So back objects in the decreasing order of pi by wi. Decreasing order of or sequence of profit per weight. So you compute this real values, keep on packing, and maybe the last object you take, maybe some fraction of it you take, so that the total capacity is exactly C. So like other greedy algorithms, so this is the greedy algorithm. I leave it to you. This is the greedy algorithm. Prove its correctness. This is an algo 1 question, so I leave it to you. Okay. So this is natural, right? Per unit weight, whichever gives you the maximum profit, you first pack those things. Convinced? Yeah, I hope so. So now let us look at this equivalent decision problem for the 0-1 version of knapsack. So suggest something. Yeah, tell something.
So like, can fractions be irrational in this case?
Irrationals. No, these are all integers. Oh, did I not mention it? Yeah. Okay, so let's say W1 through Wn are integers. So I forgot to mention these are integer weights and these are also integer values. Capacity is also, let's say, integer valued. We are not doing anything. Although here I am using floating point calculations, but the inputs are all integers. So I forgot to mention that these are integers. Yeah. Although actually it is not needed. Weights may be floating point values, but anyway, let's specialize to integer things only. Yeah, I think I have not written deliberately. These are not needed to be integers. Anyway.
So, sir, like floating point numbers are also rational, right? Because they have a fixed width.
Yeah. Yeah, they have fixed precision, so only rationals you can. So that's why I mentioned, because the complexity of the problem does not depend on whether these weights or floating point values are truly infinite precision, real numbers or whatever. Let's assume that these are integers, although this is not needed.
So for given capacity, for given total weight k, can we fit it?
No, that is constant, right?
No, I mean, given k, can I fit objects of weight k into the knapsack?
I do not understand your question. If the capacity is not exceeded, you can.
Okay. Oh, okay. I see. So given profit P, can we achieve the profit P?
Yeah, so that's the question. Okay. So given the same things, these weights W1 through Wn, profits P1 through Pn, and the knapsack capacity C, and some target profit T, decide whether the profit, I would not say exactly equal to T, that's not a good idea. In fact, why? We will see. I will say profit greater than equal to T, that is the target, can be achieved. Equality is not a good option here. Perhaps. Okay. Whether a profit greater than equal to T can be achieved. Okay, so we have to prove this equivalence. That is, this decision version can be solved in polynomial time if and only if the optimization version can be solved in polynomial time. So OPT implies decision. This is always obvious. We can solve the optimization problem and find the optimal profit and just check whether it is greater than equal to T. What about the converse? If the decision problem can be solved in polynomial time, then the optimization problem can also be solved in polynomial time. So profits are integer valued. And T can also be assumed to be an integer. Okay, so I will first tell you something. Like the previous equivalence proof, I can call the decider for target equal to 1, 2, 3, and so on until it says yes. What is the running time of this optimization algorithm? Yeah, you should tell. What is the running time of this Optimization
Summation of all P into
the running time of the decider. Good. So this running time is big O of P1 plus P2 Pn times the decider's running time, which may be d of n. This is a polynomial in n. So is this quantity polynomial in the input size?
no, sir.
No, right? Because it depends on the values rather than their bit sizes. In fact, if P max is the maximum profit, this is same as big O of n P max dn. So this factor of n is perfectly harmless, but P max is a value, not its size. So this is not a good way of invoking the decider to solve the optimization problem, because you end up in potentially exponential running time. So first let me know, is it clear to you why this is not polynomial in the input size? Yes or no? If you have a query, let me
Yes,
know.
sir.
Okay, so you understood. Anybody else? Do you have any problem in accepting that this is not a polynomial behavior? This is similar to max flow, right? Should not depend on the value. Yes or no? Okay, then how do you prove this?
The binary search on that part.
So binary search, what will you do? So do binary search instead. And then what will be the running time? Instead of this, you are searching in the range 1 or 0 to this quantity. These are all integers. So if 0 says yes and this quantity says no, then next time you take this plus this by 2, but take the integer value. Maybe floor or ceiling, whatever you like. So what will be the total running time? So instead of this linear in this, it will be logarithmic of this, right? And this can be bounded by n times the maximum profit. So this will be log of np max times d of n. And that is fine, right? Whenever you have log p max, this is now proportional to the size of p max. Because you need those many bits, log 2 p max bits. So here you do not have the option of using this kind of linear search. You have to use something like binary search. Happy? Okay. So the final part. So why is this NP complete? Okay, any suggestion from where should I reduce? Okay, first of all, it is in NP, that is clear. I am not telling. Just give me the objects to pack. I will find out whether the sum is less than or equal to C and whether the sum of the profits is greater than or equal to the target T. That's fairly straightforward to verify. So what about hardness, NP hardness? No suggestion? No, I do not see or hear any suggestion. So let us okay, so by knapsack, I mean the 0-1, the decision version of the 0-1 knapsack problem. So what is the input for partition? A1, A2, n positive integers with A equal to summation AI equal to 1 to n if n. So on this, I have to supply some number of weights, an equal number of profits, and the capacity and the target profit. Looks too tricky. Okay, okay. The weights will be same as A1, A2 through AN. Profits will also be A1, A2, AN. What should be the knapsack capacity?
A by 2.
A by 2. And what should be the target profit? Minimum target profit?
A by 2.
Again, A by 2. So it's not exactly target profit, minimum target profit. So if this partition problem has a solution, so there is a sub collection. I simply pack these sub collections, the objects in that sub collection. So the sum is equal to a by 2, so the capacity constraint is not exceeded. Okay, the sum is equal to a by 2, should be less than equal to c, so it's fine. Moreover, the total profit will also be equal to a by 2, which is greater than equal to t. Okay. So if partition problem has a solution, then this instance of the knapsack problem also has a solution. But I have to prove the other implication also. So suppose that this instance of the knapsack problem has a solution. So which is nothing but pack, say, object AI1, AI2, AI3 up to, say, let's say AIK. The capacity constraint says that the summation of this AIKs, AIJ, let's say, j equal to 1 to k, should be less than equal to c, which is a by 2. And since this target profit is achieved, so that means that summation of Aij, j equal to 1 to k, should also be greater than equal to t, which is equal to a by 2. So therefore, less than equal to a by 2, greater than equal to a by 2, it has to be exactly equal to a by 2. So that subcollection solves the partition problem. Yes or no? Happy, right? So this is a less than equal to c, and that is a greater than equal to t. Okay, so I am just making both the things work, and therefore the sum has to be equal to a by 2 exactly. Happy? Tell something, yes or no?
Yes, sir.
Yes, sir.
Okay, fine. Okay, so it's already 4:50 almost. Maybe let's see what is the next one. Oh, I see. Okay, let us see. So let G be an undirected graph and K a positive integer. You have to determine whether the removal of, you choose this, if you choose some of the edges, at most K of them, just remove them from the graph. It makes the graph bipartite. So prove that this problem is NP complete. So this is already a decision problem. Is it possible or not? And of course, the corresponding minimization problem is remove as few edges as possible in order to make G bipartite. But anyway, let's start with the with the decision version itself. It is in NP that is obvious. You just specify which edges I want to remove, and I check for bipartiteness. So that can be done in polynomial time, right? Bipartiteness checking can be done in polynomial time. Do you agree or not?
Yes, sir.
Okay, good. Yeah. So why is it NP hard? Yeah, any suggestion? What is the natural problem from which I reduce? No?
The max cut problem probably.
Yeah, this is essentially the max cut problem in disguise. This is G and some K. So you are asking for whether there exists a cart of size greater than or equal to K. So now you are asking the question. Okay, so this is the instance G M minus K, where M is the number of edges of G. Okay, so let's think of this G. There is a cart, thus that there are K edges here. Okay, if I remove remaining M minus K edges, which connect vertices of this part, like this or this part, then the graph becomes bipartite. And conversely, if by removing this, I can have a bipartite graph, then this is definitely a cart of size K. So this is essentially the same problem. Yes?
Yes, sir.
Oh,
Yes, sir.
okay. Again, this is something. So weighted max cut problem. But now instead of, I would say, trying to maximize the number of edges across the cart, I am trying to maximize the number of, the sum of the weights of the edges in a cart. If necessary, you can assume that these things are positive integers. Okay, so if I have a cart like this, I will add the weight of this plus weight of this plus weight of this plus weight of this and so on. And that sum I want to maximize, or given K, I just ask the question whether G has a cart of weight greater than or equal to K. So why is this NP complete? No suggestion? Yeah. I had a few more things, but anyway, I will stop after this. So, suggest. No. Why is this so difficult? So what is the unweighted variant of max cut? That is the max cut we have already studied, right? And that is already NP complete. So this is even a generalized version. How can it be easier than that special version? So this is also NP complete, but in order to make it very precise, I just propose a reduction from max cut to weighted max cut. So G K, this maps to G. So weights I have to specify K. So take all edge weights. Equal to what?
1.
Okay. That's it. So this is actually a very special, a generalized version. So it cannot be easier than the special version, because you can anyway convert an instance of this to the special version. This to this in the form of this generalized version. Okay. So that's the formal proof. Anyway, I had a few other things remaining, but it's already past 5. So I think I stop here. If needed, I will cover these things in the next class, along with some approximation algorithm exercises. Okay, so let me stop. If you have a query, let me know. Okay, so let me stop this sharing. Yeah. Any query on today's topics? No. Okay, then bye.
Thank you, sir.
Bye. See you next week, next Monday.